Right. You're welcome. I promised you that we have to look at very many questions to understand the concept of complex ion formation. And here is another question. So it's a matter of retrieving with the other steps that we looked at under the experiment or when we were determining it experimentally. And then we retrieve using those all steps to come up with the value of n. So here is the question. You should be, in your mind, you should be having these steps, knowing that when you get a metal ion solution, aqueous, you have to add the organic solvent, and you shake, the layers will separate, pick an organic layer, titrate it, get the concentration of ammonia, because ammonia will distribute itself in the aqueous and the organic, so pick the known volume of organic, titrate it with a certain acid, get the concentration of ammonia in the organic layer. That is one. Two, now we need to get the concentration of free ammonia, which we get from Kd times the concentration of ammonia in the organic layer. Then after that, you titrate. Now the aqueous layer, you titrate it with the same acid. Still, you will get the total ammonia present in the aqueous layer. And then you can, as easy as possible, get the concentration of the complex ammonia by getting the total ammonia in the aqueous minus the free ammonia. Then after getting that, you can easily get your value of n by getting the concentration of complex ammonia over the concentration of the ion. Now, looking at this, we have ions of metal M react with excess ammonia to form a complex according to that equation. 25 cubic centimeters of ammonia solution was added to 25 cubic centimeters of 0.1 molar aqueous solution of metal ions. So they have given us molarity of the metal ions as 0.1. Because I'm going to wrap this to another page, so I would love that we can write the question so that when I'm interpreting it, you don't be lost. So the molarity of the aqueous metal ion, or the molarity of M plus, is 0.1, all right? Followed by 50 cubic centimeters of trichromethane. The mix was shaken, allowed to reach equilibrium. The aqueous layer required 27 of 1 molar nitric acid. Okay, so if we get the concentration of, if we have the nitric acid, we can easily get the ammonia, all right, because ammonia reacts with the nitric acid from ammonium nitrate. So we can get the concentration of ammonia as a result. Then they are saying that trichromethane required 18 of 0.05 molar nitric acid. So still here we can get the concentration of ammonia in the trichromethane layer, right? Good. So here you need to know the volume. This is the volume of aqueous, and this is the volume of the organic, all right? So they want you to calculate the concentration of ammonia in the organic layer or the trichromethane layer. This is as easy as you can see, because ammonia, first of all, reacts with nitric acid from ammonium nitrate. That is one. But you're given the information of organic layer. They say that trichromethane layer required 18 of 0.05 moles. So get moles of nitric acid, write the equation between nitric acid and ammonia, get moles of ammonia. After getting moles of ammonia, you have got what the trichromethane layer holds, 50. So if 50 cubic centimeters would be containing the moles you will have gotten of ammonia, what about 1,000? That will give you the concentration of ammonia in the trichromethane layer. Then you go ahead to look for the one of water. Okay, you go ahead to look for the one of water layer. But when you're considering the volume of water, you're saying that 25 cubic centimeters of ammonia solution was added to 25 cubic centimeters of aqueous. So the total aqueous will come to be 50 cubic centimeters. It will come to be 50 cubic centimeters. All right, so now looking at all this, we can start on our question. Can start on our question. And they need concentration of ammonia in trichromethane layer. So our step is to begin with this. 1,000 of 1,000 centimeters of nitric acid contain these moles. What about 18? Okay, so we shall say for Roman 1, we shall say that 1,000 cubic centimeters of nitric acid contains 0.05 moles. All right, so if that is the case, then what about if that is the case, then what about what about the other volume was 18? Okay, so there we shall be looking for the number of moles in 18 cubic centimeters. So we shall say what about 18? Cubic centimeters of nitric acid contain 0.05 times 18 out of 1,000 moles. And this is going to become 9 times 10 to the power exponent to the power 4 moles. These moles you've gotten are moles of nitric acid. Now we can write the equation to get moles of ammonia reacting with nitric acid shall get ammonium nitrate. So by mole ratio, you can see that 1 mole of nitric acid reacts with 1 mole of ammonia, implying that thus the moles of ammonia reacting will be the same, 9 times 10 power negative 4 moles. So after getting moles of ammonia, they told me that 50 cubic centimeters of trichloromethane. So it means that 50 cubic centimeters of trichloromethane contain 9 times 10 to the power negative 4 moles. Then what about 1,000? This one will give me the concentration, write all the words here, contain 9 times 10 to the power negative 4 times 1,000 out of 50 moles. So I am going to get the total moles as 0.018 molar. That is first part is done. Then I want us to get the concentration of ammonia that formed a complex. You cannot get a concentration of ammonia that formed a complex when you don't have the concentration of free ammonia. But in other words, anyway, let's first get also the concentration of ammonia in the aqueous layer or total ammonia. Okay, so part 2, we go for aqueous part now. For aqueous part, they told us the aqueous layer required 27.5 of 1.0 molar nitric acid. So if we are, since we have 1.0 molar nitric acid, we shall be saying that 1,000 cubic centimeters of nitric acid contain 1 mole. What about 27.5 cubic centimeters of nitric acid will contain 1 times 27.5 out of 1,000 moles. And this one will give us, these moles would be 0.0275. moles. So by mole reaction ratio, still 1 mole of nitric acid reacts with the 1 mole of ammonia, implying that moles of ammonia reacting are going to be 0.0275. But they told us that initially that 25 cubic centimeters of ammonia solution was added to 25 cubic centimeters of aqueous. So the other solution was added to aqueous solution of metal ions, so making the total aqueous solution having volume of 50. So I shall say 50 cubic centimeters of aqueous layer contain 0.0275 moles. What about 1,000 cubic centimeters of aqueous layer will contain 0.0275 out of 50 times 1,000. Do it from first principles by writing all the words. And this is going to give us 0.55 molar. Now, this is the molarity or the concentration of ammonia in the aqueous, or concentration of total ammonia. Okay. Now we have organic, we have total ammonia, but we know that to get concentration of complex ammonia, which they want, we get the concentration of ammonia, total ammonia in aqueous, okay, total in aqueous, we subtract the concentration of free ammonia. So this is going to be, now we don't have free ammonia. So let's first get free ammonia. Concentration of ammonia free. We say that to get free ammonia, we get Kd, we multiply the concentration of organic ammonia in the organic layer. So the Kd was given as 25, then the concentration of organic layer, which is 0.018, and this one will give us 0.45 molar. Now remember, we need the complex ammonia. So the concentration of complex ammonia is going to be equal to ammonia total, which is 0.55 in aqueous, minus free ammonia, which is 0.45. And this is going to give me 0.1 molar. So the concentration of complex ammonia is 0.1 molar. Then part 3, they want us to get the value of N. But to get the value of N, we need to determine the concentration of the metal ion. And since we have the complex, then it is very, very easy. So we are going to say, remember the concentration of ammonia, I'm doing part 3, the concentration of ammonia that form the complex, we've gotten it as 0.1 molar, but they need the value of N, which value of N is gotten from the concentration of complex ammonia, all right, out of the concentration of the metal ion. In this case, it is M+. So we need to first see, do we have the concentration of the metal ion? So how do we determine that? We are told that 25 cubic centimeters of ammonia solution was added to 25 cubic centimeters of 0.1 molar aqueous solution of metal ions. So we have to remember that if we are given, because we need to get the concentration of the metal ion in the aqueous solution, right? So we shall say that 1,000 cubic centimeters, okay, 1,000 cubic centimeters of a metal ion contain metal ion solution contain 0.1 1 moles. Then what about 25 cubic centimeters? Of that metal ion will contain 0.1 times 25, everything out of 1,000 moles, okay? So these moles are going to be equivalent to 2.5 times 10 to the power negative 3 moles. So these are moles of the metal ion. But these metal ions, okay, within the metal ions, we added 25 centimeters of ammonia to the very 25, so it became 50 in total in aqueous solution. So we shall say 50 cubic centimeters of aqueous solution or aqueous layer, let me say aqueous layer, will be containing the 2.5 exponent negative 3 moles of M plus ions. Then what about 1,000? So the 1,000 cubic centimeters will contain 2.5 exponent negative 3 times 1,000 out of 50 moles. So these moles are going to come up as 0.05 molar. Okay, this is a molar concentration of the M plus ion. So now I've gotten the moles of the metal ion, the concentration of the metal ion. I have the concentration of the complex ammonia. It means that 0.05 moles of M ions are complex with the 0.1 molar of ammonia, okay? So one can substitute in the formula, or else one can also say that 0.05 moles of M ions complex with 0.1 moles of ammonia. What about 1 mole? 1 mole of a metal ion will be complexing with 0.1 over 0.05, of course, times 1 moles. And this one will give you 2 moles of NH3. So that's the value of N. Hence, N is equals to 2. Substituting in the formula still gives you the same answer. Right. Let's do some other example here. It's a bit lengthy, but the same approach. Same approach. 3 25 cubic centimeters of excess ammonia solution were added to 25 cubic centimeters of 0.1 molar copper 2 sulfate solution, and the resultant solution shaken with trichloromethane. After the layers had settled, after the layers had settled, 50 cubic centimeters of trichloromethane layer needed 25.5 cubic centimeters of 0.05 molar hydrochloric acid for neutralization, while 20 cubic centimeters of the aqueous layer required 33.3 cubic centimeters or 0.5 molar hydrochloric acid for neutralization. KD for ammonia between water and trichloromethane is equals to 25. Determine the formula of the complex ion formed. Wow. Now for this case, they have not given you bits. They have not given you the question in bits. They have given it at once, determine the formula of the complex formed. But for you, you should be knowing the steps to take. You should be knowing that I need to first determine the concentration of acid. You need to first get the organic layer. Okay, you need to first get the concentration of the organic layer. All right, concentration of ammonia in the organic layer. So since they have given you what the organic layer required, they said 50 cubic centimeters of the organic layer needed 25 of 0.05 molar hydrochloric acid. So in other words, here, first get, we're just going to break it down for you because I want you to do it using the advice I'm going to give. First get moles of hydrochloric acid. We are working on the organic layer first. Moles of hydrochloric acid would be equal to, of course, 0.05 times 25 over 1,000. We'll give you the moles of hydrochloric acid. After getting moles of hydrochloric acid, you write the equation. You know that ammonia reacts with the ammonia solution. Aqueous reacts with hydrochloric acid. Aqueous to form ammonium chloride. Aqueous. Now, you can, after getting moles of hydrochloric acid, you can get moles of ammonia. So moles of ammonia by mole reaction ratio, they are going to be equal to moles of hydrochloric acid. After getting moles of ammonia, then you start 50 cubic centimeters of trichloromethane contain those moles of ammonia you've gotten. What about 1,000? That one will give you the concentration of ammonia in the organic layer. After getting the concentration of ammonia in the organic layer, now you can move to aqueous layer. Without stopping, because this question, they have not said first calculate this or this. No, you are going to go straight up to the value of n. So for the case of aqueous layer, they have told you that 20 cubic centimeters of the aqueous layer required 33 cubic centimeters of 0.5 molar hydrochloric acid. So first get moles of hydrochloric acid also here. So get moles of HCl. After getting moles of HCl by mole ratio, they will be the same as moles of ammonia. They'll be the same as moles of ammonia. So after getting moles of ammonia, all right, after getting moles of ammonia, then now they are saying that 20 cubic centimeters of aqueous layer. Okay, 20 cubic centimeters of the aqueous layer. Okay, 20 cubic centimeters of the aqueous layer. So you have the aqueous layer. The aqueous layer has 20. So we'll be saying that 20 cubic centimeters of the aqueous layer, all right, contain, they will be containing the moles you've gotten here, moles of ammonia. 20 cubic, because when this ammonia, when you have aqueous and the organic layer, ammonia has distributed itself between that two. So you've gotten moles of concentration of ammonia in organic, now you're looking for concentration of ammonia in aqueous. So 20 cubic centimeters of aqueous layer will be containing the moles of ammonia you've gotten here under aqueous. Then what about 1,000? You get moles of aqueous layer, moles of ammonia in aqueous layer. And that one should be moles in aqueous. You'll calculate and see if you'll come up with 0.8325. 8325. And here for organic, you calculate and see if you come up with the 0.2, actually 0.0255 molar, 0.8325 molar. After getting aqueous and organic now, life becomes very, very, very easy. Now you go to get the ammonia, which is complexed. But to get complex ammonia, you get total aqueous, total ammonia in aqueous. You subtract ammonia free. Okay, so this one, now we'll need it first get free ammonia. To get free ammonia, we've said that we get Kd times concentration of ammonia in organic. And I want you to check if you come up with 0.6375, all right, molar. After getting concentration of free ammonia, now we substitute it there. I want you to check and see if you'll come up with the ammonia complexed as the ammonia complex should be 0.195 molar. Now, after getting ammonia complexed, you can get your value of N, because remember N is equals to complexed ammonia out of concentration of copper in aqueous. Now what you do, you have to first get a concentration of aqueous copper, concentration of copper in the aqueous. Remember they said that 25 cubic centimeters of excess ammonia were added 25 cubic centimeters of 0.1 molar copper 2 sulfate, meaning that the total aqueous is having 50 of copper 2 ions. All right. So first get moles of copper in aqueous, and those are going to be 25 times 0.1 out of 1,000, you get 2.5 exponent -3 moles. Then after that, the total aqueous has 50 cubic centimeters, 25 plus 25, 50 cubic centimeters of aqueous contain these moles of copper. What about 1,000? So you get molarity of copper ions as 0.05 moles. So this is the concentration of copper 2 ions. Now it means that 0.025 moles of copper 2 ions complex with the 0.195 moles of ammonia. Then what about 1 mole of copper 2 ions? You'll get your answer as 4. So the formula of the complex, if they say determine the formula of the complex, it will be Cu NH3, the value of N is 4, then 2 plus. So that is the formula of the complex after having gotten a 4. 4 is the number of ligands, or the ammonia molecules, the number of ammonia molecules that coordinate with copper 2 ions to form, or that coordinate with this metal to form a coordination complex of tetramine copper 2 ion, right? So that is what we get. I do guess everyone has followed it very, very, very well. Before I go to a graphical part of the question, we can also be examining a case where we have to do with extraction, or where we have to do with the ores of substances. So I'm going to take you through that question also, and that would be our example number 4. 8 grams of an ore of zinc was dissolved in excess ammonia and the resultant solution was diluted to 1 liter with water, shaken with the trichloromethane and left to settle. Okay, then they are saying that 50 cubic centimeters of trichloromethane layer required 25 cubic centimeters, 0.05 molar hydrochloric acid for complete neutralization. For complete neutralization, while 25 cubic centimeters of aqueous layer required 40 cubic centimeters of 0.5 molar hydrochloric acid. KD for ammonia between water and trichloromethane is 25. Calculate the 1 concentration of zinc ions in the complex formed. 2 percentage of zinc in the ore. So really, like the way we did the other question, the same applies here. Okay, it's the same applies here. Now, this one I'm going to do it all because I don't want us to get issues with it. Okay, now let's first work on the organic layer. For 1 moles of HCl used in the organic layer, trichloromethane, would be equal to, they say that 25 cubic centimeters of 0.05 molar hydrochloric acid. So 0.05 times 25 out of 1,000 moles, and these moles are going to give us 1.25 times 10 to the power negative 3 moles. After getting these moles, by mole reaction ratio, we can get moles of ammonia. And it's very, very, very crucial to write the equation plus HCl to give us ammonium chloride. The fact that 1 mole of HCl reacts with the 1 mole of ammonia, it means that moles of ammonia in CHCl3 are 1.25 exponent -3 moles. So you've gotten moles of ammonia in the trichloromethane layer, all right? So we can get the concentration of ammonia in the trichloromethane layer because they say that 50 cubic centimeters of the trichloromethane layer, and the trichloromethane layer has 1.25 moles. So it means that 50 cubic centimeters of trichloromethane layer contain 1.25 times 10 to the power -3 moles. Then what about 1,000? 1,000 cubic centimeters will give us the concentration 1.25 times 10 to the power -3 out of 50 times 1,000. So this is going to give us 50 to 50. Here we have 20 times this, 1.25. It is going to give us 0.025 molar. This is the concentration of ammonia in the organic layer. Let's go ahead to look for concentration of ammonia in the aqueous. All right. Now, moles of HCl in aqueous layer. They say that 25 cubic centimeters of the aqueous layer required 40 cubic centimeters of 0.5 molar hydrochloric acid. So they're going to be 0.5 times 40 out of 1,000. Because you'll be saying that 1,000 cubic centimeters of hydrochloric acid contains 0.5 moles, then what about 1,000? All right, so these moles are going to be equal to, they're going to be equal to 0.02 moles. Now, after getting these 0.02 moles by mole reaction ratio, still 1 mole of HCl react with the 1 mole of ammonia, implying that moles of ammonia still are the same as 0.02. So moles of NH3 are equaling to 0.02. That is in aqueous, but they're saying that 25 cubic centimeters of aqueous, meaning that these moles are in 25 cubic centimeters of the aqueous layer. Then we need moles in 1,000 cubic centimeters. So I will be saying that 25 cubic centimeters of aqueous layer contain 0.02 moles of ammonia. What about 1,000 cubic centimeters of aqueous layer will contain 0.02 times 1,000 over 25. So this is going to give me the moles as 0.8 molar. So my aqueous layer has got this. In other words, in summary, the concentration of ammonia in the organic layer, we got it as 0.025. And we got a concentration of ammonia in aqueous, which gives us the total. That is 0.8 molar. So from here, we calculate the free ammonia in aqueous, and this is going to be equal to Kd, which is 25, times the concentration of organic. Better state the formula, Kd times concentration of ammonia in the organic layer. So times 0.8 0.025. This one gives us 0.625 molar. After getting the concentration of free ammonia in aqueous layer, we can get the concentration of complexed ammonia. So ammonia complexed is going to be equal to, for complexed ammonia, we get ammonia total or total ammonia, right? We subtract concentration of free ammonia, and this is 0.8 minus 0.625, giving us 0.175 molar. This is the complexity ammonia. But remember, the question is the concentration of zinc ion. That is where I come up and write my equation of zinc complexing with the ammonia. So when zinc ions complex with ammonia, we shall form a complex of tetramine zinc 2 ion, and this 4, we bring it here. So what would it mean? It would mean that 4 moles of ammonia complex with 1 mole of zinc, all right? 4 moles of ammonia complex with the 1 mole of zinc ion. So if 4 moles can complex with 1 mole of zinc ion, what about 0.17 moles? 0.175 moles will complex with the 1 times 0.17 out of 4. And this one will give you 0.04375 moles of zinc ion. But remember, we use the concentration, moles which were in a liter. So the same applies to this. The concentration of zinc ion is going to be 0.04375 molar. And that is it. Then they wanted us to get the percentage of zinc in the ore. The ore had got 8 grams, right? The ore had got 8 grams. The ore had gotten 8 grams. The whole ore is having 8 grams. But here we've gotten the concentration of zinc ion in the ore. All right? Is it? We've gotten concentration of zinc ions in the complex form, sorry, in the complex. So we can get mass of pure zinc in the ore. Part 2, we can get mass of pure zinc in the ore. To get mass of pure zinc in the ore, we shall get the concentration 0.04375. We multiply by the relative atomic mass of zinc, which is 65. 0.04375 times 65. This one will give us 2.844 grams. But we need percentage of zinc. So percentage of zinc is going to be equal to mass of zinc in the ore, 2.844, over the total mass of the ore, 8, times 100%. Well, this is going to give us 35.55%. So that is it. That is what we get. That is what we get. Right? So it can be applied in many other cases. Let me do my final example, and this one has some graphical concept. It has a graphical concept. It's about cobalt. That is my example 5. Cobalt, 2 ions. Cobalt 2 ions form a complex form a complex CO. Okay, so the table below shows the results of partition. So the result of partition of ammonia between 0.1 molar cobalt to sulfate and trichloromethane. So we have ammonia concentration in 0.1 molar cobalt to sulfate, and we also have ammonia concentration in trichloromethane. Wow, so here we have 0.72, we have 0.01, 0.94, 0.03, 1.19, 0.05, 1.43, 0.07, 1.70, 0.09, 1.92, 0.11. So that is my table showing the results of partitioning ammonia between cobalt 2 sulfate and trichloromethane. The first part of the question is plot a graph of ammonia in 0.1 molar cobalt 2 sulfate against the concentration of ammonia in trichloromethane. 2, determine the value of N, determine the value of N in the complex. I'm going to guide you on how to go about this question because I'm not to scale, but I'm going to guide you now to do this question. Of course, one title of the graph, a graph of ammonia concentration in 0.1 molar cobalt 2 sulfate against concentration of ammonia in trichloromethane. You have to put a title. 2, you have to draw using the very best appropriate scale, the appropriate scale. So you have to look at the scale and then the axis. Then your plotting will matter. And then your shape will matter. The fact is, for this case, you must come up with a straight line. I'm sketching something here. We are having a concentration of ammonia. Here we shall have concentration of ammonia. All right. Then in 0.1 molar cobalt sulfate. Here we shall have concentration of ammonia in trichloromethane. So now, remember, we need to get, for you to get the value of N, you need the complexed ammonia. You need complexed ammonia. To get complexed ammonia, or to get the number of moles that complexed with 0.1 molar solution of cobalt to iron, okay, we need the intercept. In other words, as you plot, you're going to come up with a graph in this shape or graph in this format. Implying that if we need the intercept on Y, if we need an intercept on this concentration, because we need the concentration of ammonia that complexed with the cobalt, meaning we need the concentration of ammonia on the cobalt axis, okay? It means that this one must start with a 0, since we need the intercept here, because we need the value to read here. So we shall extrapolate this line up to this point in order to pick the value of the concentration of ammonia that complexed with the cobalt 2, all right? So it means that if we need the intercept on y-axis or the axis of cobalt, we begin with this, we begin the axis of ammonia in trichloromethane with 0. So here you can start from 0.0, 0.01, 0.02, something like that. Appropriately, you can put the suitable scale that you would really need. So we extrapolate to get the value here. Another thing, this one here will give you the number of moles, of course, to give you the number of moles, or to give you the complexed ammonia, all right? And to my observation, according to whatever you will get, because you already have the concentration of cobalt at 0.1, I expect you to pick a value like 0.6. I expect you to pick 0.6 as you plot scale and see the value you will come up with, okay, on this axis. So, after getting that value, remember at the intercept, the concentration of ammonia in trichloromethane should be equal to 0. That is why we've started this axis to 0. The fact that we need the concentration of ammonia in cobalt that complexes with the cobalt, it means that we need to read it on this axis. Therefore, the other axis must begin with the as 0. Okay, that one means that therefore all the ammonia present has complexed with the cobalt. Now, if we get the complexed ammonia as 0.6, then it would mean that, and you know that the cobalt, this is small o, the cobalt concentration is 0.1, then really you can get the concentration, you can get the value of N, because you'll be saying that 0.1 mole of cobalt ions complex with the 0.6 moles of ammonia. What about 1? 1 will complex with the how many moles of ammonia? 0.6 over 0.1, which will be 6 moles. And the moles you've gotten, because that they are the moles of ammonia, it means that the number of moles of ammonia are 6. All right. So it means that for cobalt to complex with the ammonia, we need 6 molecules of ammonia. All right. So that is it. That is it. I wish you all the best. And just something small left is how to determine the equilibrium constant Kc using partition law. All right. How to determine the partition coefficient, and still distinguishing between bromides and iodides. Maybe I can go through the one of distinguishing between bromides and iodides, so that in the next video I summarize how we get the Kc, the value of Kc. All right. But for this case, when we are distinguishing between bromides and iodides, it means that to the test solution, let me summarize it, how we distinguish between bromides and iodides. Distinguishing between bromides and iodides. What we do to the test solution, because we want to distinguish between these two, meaning to the test solution that has got these two, we add dilute nitric acid to the test solution. We add dilute nitric acid to the test solution, followed by a bleaching powder. One can use calcium hypochlorite, and a bleaching powder, using bleaching powder. Okay, we add bleaching powder. Then after, remember you add to the test solution, you've added dilute nitric acid followed by bleaching powder. Then after a while, you're going to add an extracting solvent, and that is the tetrachloromethane, rather trichloromethane. Let's use tetrachloromethane. We shall add tetrachloromethane. Then the mixture will be shaken and allowed to stand or to settle. Now, formation of a brown coloration. Formation of a brown coloration in the tetrachloromethane layer shows the presence of bromide ions, okay? And while the formation of purple coloration shows the presence of iodide ions. That is how we can distinguish between bromides and iodides in this particular case. Okay, simple. To the rest solution, add dilute nitric acid, bleaching powder followed by carbon tetrachloride or tetrachloromethane. Then let the mixture settle for some good time. You are going to see a brown coloration forming. It will imply that a bromide ion is there. You will see a purple coloration and you will conclude that that is an iodide ion present. So let's meet in our last part. This was part C. So in our last part, we shall be looking at determination of the equilibrium constant, case C, and then we call it a day.